Hello again. So today we're going to be looking at a different application of integration. Now, from the past, we know that the geometric meaning of the integral, so the integral from a to b of some f of x function dx, that tells us the area under the curve, so the area above the x-axis under that curve from that lower bound to that upper bound. And we would go through the process of integration before we had some different means of estimating integrals if we didn't have a set function. But what we're going to be looking at today is what happens when we've got two functions. And it's not just the area above the x-axis below a curve, but between two different curves. So now we've got a top curve, I'm labeling that f of x. We've got a bottom curve, I'm labeling that g of x. We want the area all the way between those. So that's the above, the below. Sometimes we've got both sides are positive, so we want to get rid of something. Well, maybe intuitively, it's the area between. What we're going to be doing is subtracting. Now, I'm going to take a look at how we defined our definite integral before. What we did was we used a limiting process. So before, we took some delta x, some thickness, and we had some height here where that was f of x of I star, however we defined that. And so we defined our integral as the limit as the number of rectangles approaches infinity. And we added all of those rectangles. So from I equals 1 to n of f of x I star multiplied by dx. So we had the height, value of the function, multiplied by the width of the rectangle. That gave us our definite integral. So that's how we defined that. Maybe intuitively, it makes sense that, well, our width of the rectangle is going to be still some delta x, but our height is, that difference from the top to the bottom. So we're going to take the same idea. We've got our width of a rectangle. Our height of a rectangle is now going to be the difference from the upper curve to the lower curve. So it's going to be the upper curve subtract the lower curve. And we would repeat that process with an arbitrary number of rectangles. Down at the bottom, that gives us our limiting factors. We can define that area between the curves as the limit of the sum as our rectangles approach infinity. And so when we have this, we can generalize or turn this into our definite integral, the area between the bounded curves, so that f of x and, that should be g of x there. The lines x equals a and x equals b, so that's our lower bound and our upper bound. Now here I'm saying where f and g are continuous, so we can't have any breaks in those curves. And also we are saying that f is above g. It's going to be the upper curve subtract the lower curve. The area between them, I think it makes sense, is going to be the integral of the differences from the left bound, from the lower bound to the upper bound. Let's try this out. So first example, we're going to find the area of this region. So it's bounded above by the curve y equals x, bounded below by the curve y equals x, and we're bounded on the left and the right sides by 0 and 1. So we've got this upper curve, this lower curve. Now, thinking about this, we want to get rid of all of this. We don't need that space anymore. Well, we're going to be subtracting it anyway. So in a way, if we just take the integral from 0 to 1 of e to the x dx, that is all of this. If we're just taking the integral from 0 to 1 of x dx, that is this triangle down below. And so kind of intuitively, it makes sense. We are subtracting that amount. So let's combine this into a single integral using that previous idea. So this area is going to be defined as the integral from 0 to 1. That's our left to our right bounds, or our lower and upper bounds. We're going to take the upper curve, e to the x, subtract the lower curve, x. And that is an integral that we can evaluate. This gives us e to the x, subtract 1/2 x squared. We're going to evaluate from 0 to 1. So we plug in 1, we're going to have e, subtract 1/2. Subtract, we're going to have 1, subtract 0. And so in total, our area is going to be e, subtract 3/2. Not too bad. What we're using is we're actually applying something called Cavalieri's principle, where we can actually shift or rearrange these rectangles. Think about like a stack of coins. So if we've got a stack of coins, it's got a set volume. But if we take our stack of coins, so draw that out there. We've got our stack of coins where all those coins are there, and I kind of put them at an angle, or if I skew them, all those coins are now pushed over. It's going to have the same volume because it's still the same coins. It's just in a different way. So we're taking all those heights, and we're just kind of shifting them down so they are adjacent to the x-axis. In short, area, top curve, subtract the bottom curve. Let's try the next one. Find the area of the region enclosed by those two parabolas, y equals x squared and y equals 2x minus x squared. Now, I know that our bottom curve is y equals x squared. And I know that because I know the graph of y equals x squared. I know that our top curve is y equals 2x subtract x squared. So it follows then our area between is going to be the integral of the top curve, 2x subtract x squared, subtract the bottom curve, minus x squared, dx. Ooh, I can simplify or rewrite that. That's going to be 2x subtract 2x squared. It's going to be, oh no, we don't know the bounds. We're going where those two intersect. So there's our lower bound, there's our upper bound, A to B. We need to figure out what are our upper and lower bounds. It's the intersection points between those two curves. So I'm going to find that by setting our two equations equal to each other. Oops. I'm going to solve. So we've got 2x squared subtract 2x equals 0. It's 2x, x subtract 1 equals 0. And so we've got x equals 0, x equals 1. So our lower bound is 0, our upper bound is 1. Now we can proceed with our integration. X squared minus 2/3 x cubed. Evaluate that from 0 to 1. If we plug in 1, we're going to have 1 subtract 2/3 minus, if we substitute in 0, we're going to have 0 minus 0. And so we've got an area of 1/3. Top curve subtracting the bottom curve. We're going to do two more. All right. So area of the region bounded by the curves y equals sine x and cos x. So I know this is cosine of x because, well, I know the cosine curve. It has an initial value, or y-intercept of 1. I know the other one is y equals sine of x because I know that sine passes through the origin. And we are going from over the interval 0 to pi over 2. So the area between those two curves. So I'm going to go integral from 0 to pi over 2 of, okay, we've got cos x, subtract sine x dx. Integrating, we're going to have sine x plus cos x, evaluated from 0 to pi over 2. And so plugging in pi over 2, we're going to have 1 plus 0, subtract, substitute in 0, we're going to have 0 plus 1. We got 1 minus 1. Uh-oh, the area is 0. Well, that doesn't make sense because clearly the area is not, there is area there. So it can't be 0. Here's what's going on. It always has to be the area at the top, subtract the bottom. At this point, pi over 4. And we know it's pi over 4 because that's a value where sine and cosine are equal. They swap. Sine is now on top, cosine is now on bottom. So it always has to be the top curve subtract the bottom curve. That's going to give us a positive value, and it's not going to cancel. Thinking about that, this is going to be a positive value. This is a negative value because if we're doing cosine the lower, subtracting a greater, well, it makes sense that that positive, that negative cancel to 0. Let's try this again, splitting this. So I'm going to rewrite this as the area 0 to pi over 2, nope, line 0 to pi over 4 of cos x minus sine x, plus the area from pi over 4 to pi over 2. On that interval, sine x is the greater curve, so sine minus cos x. So that's going to give us still sine x plus cos x, evaluated from 0 to pi over 4. We're going to add to that, we're going to have negative cos x minus sine x, evaluated from pi over 4 to pi over 2. I'm going to factor that negative, so we've got now sine x plus cos x, evaluated from 0 to pi over 4, subtract, I've got sine x plus cos x, evaluated from pi over 4 to pi over 2. So on the right side, that's going to be root 2 over 2 plus root 2 over 2, subtract 1, subtract, well, that's going to be 1, subtract, it's pi over 4, root 2 over 2 plus root 2 over 2. So we have root 2, subtract 1, minus 1, plus root 2. And so that's going to get us a total of 2 root 2, subtract 2. There we go. One last one for now. Find the area enclosed by the line y equals x minus 1, y equals x minus 1. I know that curve because, well, it's a line. And the parabola, overlap. Oh, y squared equals 2x plus 6. That's this curve over here. Y squared equals 2x plus 6. Everything's in terms of like horizontal. We recognize that's not a function, but actually it's just an equation in terms of x, or x is a function of y. What I'm going to do is I'm going to rewrite these two equations. I have x equals y plus 1. And I'm going to rewrite the second one as x equals 1/2 y squared minus 3. A little bit different now. Rather than having vertical rectangles and looking at dx, now we could do that starting here where we've got the top curve, subtract the bottom curve, but over on the right side, we'd be going from one curve to itself. So this reason I rewrote this as x equals is now we're going to think about horizontal rectangles. And making a horizontal rectangle, well, the base of the rectangle is going to be x on the right, subtract x on the left. So it's going to be the greater value, subtract the lower value will get us that horizontal distance. The height in this case of our rectangle is going to be delta y, some thickness of y. So it's going to be now integral x on the right subtract x on the left dy. And we're going to use bounds in terms of y. So we've got x on the right, we've got x on the left. We can see looking by the graph, but also by setting the two equations equal to each other, our lower bound, our lower y value is -2. Our upper y value is y equals 4. So we're going to integrate from -2 to 4. We're going to do our right curve, y plus 1, subtract our left curve, 1/2 y squared, subtract 3. Now instead of doing dx, because we have these horizontal rectangles, that's going to be delta y or dy. Same idea, it's just a different variable. I'm going to neaten this up. So I've got the integral from -2 to 4. That's going to be y, subtract 1/2 y squared plus 4 dy. And I can proceed as before. So I've got 1/2 y squared minus 1/6 y cubed plus 4y. And we're going to evaluate from -2 to 4. And I do the exact same thing as before, just substitute in. We can find that area. So from here, try it out. Let me know if you got any questions. See you later.